This is an additional example of a power series centered elsewhere. So here, since the terms of the power series are x minus 5, this means our center is x equals 0, or x equals 5, sorry. And we're going to go ahead and try to find the interval of convergence in this example. So I'm going to use the root test this time. And this is a good choice because I noticed that every single portion of this series is something raised to the nth power. So the root test will be real quick. So when I apply the root test, I take the limit as n approaches infinity of the nth root of the absolute value of the series terms, the general term that I add at the nth step. It's the absolute value of that a sub n. So in this case, the first thing to remember is that when we raise something to the nth power, that's the same as raising it to the 1 over n. And we're taking an absolute value here. The absolute value of negative 2 to the n is just 2 to the n. And then when I take the absolute value of x minus 5 to the n, that's the same as taking x minus 5's absolute value and then raising it to the nth power. And then in the denominator, I just have 3 to the n. 3 to the n is always positive. So here, let's not take up quite so much space. Next, I'm going to take the limit of that expression. I'm going to go ahead and take the 1 over n power everywhere. So the nth root of 2 to the n is just 2. The nth root of that absolute x minus 5 to the n is absolute x minus 5. And the nth root of 3 to the n is 3. So now we actually have a constant. So since nothing is in terms of n, we get that the limit we're looking at here is just 2 over 3 times the absolute value of x minus 5. And so by the root test, I need this limit. We know that that quantity needs to be less than 1 if it's going to converge. So now I'm going to solve for absolute x minus 5. So I'm multiplying both sides by 3 halves, multiplying by 3 and dividing by 2. Then if the absolute value of x minus 5 is less than 3 halves, that means x minus 5 is between positive 3 halves and negative 3 halves. And now I'm going to add 5 to both expressions. 5 minus 3 halves less than x less than 5 plus 3 halves. And that'll give me, if we want to rewrite it, a single fraction. 7 halves is less than x, which is less than 13 halves. Okay. So now I need to do my two endpoints. I have to check x equals 7 halves and 13 halves separately. And I'm going to be wiser this time, and I'm going to look and see which one of these would actually give me that positive series term first. Well, since my original series, the negative 2 to the n over 3 to the n, that started out alternating. If I want the one that's positive, that might tell me if both converge, then I'm going to want to put in the one that's going to have a negative term as well. So I'm gonna do 7 halves minus 5 first. 7 halves minus 5 to the n. So this is really the series n equals 0 to infinity of negative 2 to the n over 3 to the n times negative 3 halves to the n. And you can see that when you multiply that all through, we're actually talking about the sum of 1, adding 1 infinitely many times, which is divergent. If you will, you could prove it by the test for divergence, because you could say the nth term does not converge to 0 because the nth term is 1. But if you just write out for me that you can show that it's 1 added infinitely many times, I'm cool with you just saying that that means it's divergent. So this was the x equals 7 halves case. So we know we don't have absolute convergence there. At the other bound, let's try x equals 13 halves. That one, we're going to have negative 2 to the n over 3 to the n times 13 halves minus 5 to the n. But now we've got, this is the one with the positive 3 halves, so it's negative 2/3 to the n times positive 3 halves to the n. And that means that we're actually talking about negative 1 to the nth power. And this is an alternating series, sorry, 1 minus 1 plus 1 minus 1 plus. And that's an alternating series, but since the nth term is not convergent to 0, this also diverges. And so neither endpoint for this example will be in the interval of convergence. So the interval of convergence is only 7 halves to 13 halves, since neither endpoint caused a convergent series. Let's do one final example of finding the interval of convergence. So the first thing to notice in this example is that I haven't quite written it in the standard form of a power series centered at a particular number. It's still a power series, it's equivalent to a power series, but if you will, it doesn't formally have the right structure. The reason I say that is we said that power series should always look like this, a sub n or c sub n times, they should look like some c sub n times x minus a to the nth power. And that is not what we see here. So to understand how to rewrite it in that form, we'd need to take the 4x plus 1, and we'd want to rewrite it as 4 times x plus a fourth to the n, and then this is 4 to the n times x plus 1/4 to the n. And now we could see that this is a power series centered at negative 1/4. And we could use that as we work through the problem. But I'm going to, so I just want to point out that that's how you could determine the center. But when we go through searching for the interval of convergence, it turns out we don't have to worry about that piece. Okay, so let's go through and do that. I'm going to choose to use the root test to find this interval of convergence. So let's change ink so we can find our work real easily. Let's use the root test. Okay, so I'm going to take the limit as n approaches infinity of the nth root of the absolute value of 4x plus 1 to the nth power over n squared. Well, that's the limit as n approaches infinity of the absolute value of 4x plus 1 to the n over n divided by n squared over n squared, or n to the 2 over n, if you will. Okay, so we get the limit as n approaches infinity of the absolute value of 4x plus 1. To make sense of the denominator, I'm going to rewrite this as n to the 1 over n squared. And the reason I'd like to use that is now I can do the limit bit by bit. So this is this is absolute value of 4x plus 1 on top, divided by the limit of the bottom. And the limit of the bottom, squaring something, since the limit n to the 1 over n, that's our famous nth root of n. We said that limit's always 1. So I can actually take the square outside the limit. So this is the absolute value of 4x plus 1 over the limit of n to the 1 over n squared. And so I get absolute 4x plus 1 over 1 squared. And thus the limit is the absolute value of 4x plus 1. So now to make it work with the root test, if this is what I'm getting out as my limit, I want my limit to be less than 1 if we're going to get convergence. So I will take absolute value of 4x plus 1 and set it less than 1, which means that 4x plus 1 is between positive and negative 1. Subtracting 1 from both sides, I get that 4x is between 0 and negative 2, and therefore negative 1/2 is less than x is less than 0. This is my interval, except for maybe the endpoints for the interval of convergence. So now I need to go back and consider what happens at the endpoints. What happens when the absolute value of 4x plus 1 equals 1? Well, if it were to equal 1, why not just check the absolute convergence first? We would have the sum n equals 1 to infinity of 1 to the n over n squared, or just the sum of 1 over n squared. Now that's a convergent p-series since p is equal to 2. And by that argument, this implies that the series converges absolutely when we're at either endpoint. Converges absolutely for x equals 0, because that's when we're getting 1 on the nose, and it also converges absolutely for x equals negative 1/2, which is when the part inside the square root, 4 times negative 1/2 plus 1, that's the part inside the square root here would be negative 1. So that's why. So the interval of convergence for this case includes both endpoints, negative 1/2 up to 0. And you can go back and look at the example we did of x to the n over n squared, and you can see how similar this one is to understand the similarities.